Famous mathematician David Hilbert, in one of his radio speech in German, told that we will know and we must know. Well, as you can see, this is a very optimistic quotation by David Hilbert, who tried to axiomatize and believe that every axiomatic system is formally decidable. What is important for all of us to know is that this statement, we will know and we must know, so it actually shows that there is an optimism in terms of knowledge, in terms of our pursuit of science and mathematics. Welcome to the sixth lesson on quantum field theory, where I believe and persist on the same quotation which David Hilbert actually told, that we will know and we must know. Well, in today's lecture, what I'm going to do is that I'm going to give you a complete understanding of quantum field theory. Yeah. So I am going to sum up the entire idea of quantum field theory. I am going to tell you what are the major areas which I have covered in the lectures, and thereby by the end of today's lesson, you will give a complete and a detailed understanding of quantum field theory. It will be an enjoyable journey. It will start right from the basics and it will go back to the last class that we have ended. But I can tell you this much, that this particular, I would say, lecture series is basically meant for things which will take you more into the details and understanding of quantum field theory. So having said and done with the basic idea, let us begin and start with what we are about to start today. And I would like to first of all talk about today's lecture, which would be starting with a summation of the lectures of 1, 2, 3, and 4 and 5. So I'm going to sum up all the lectures that I have done, and you will get a complete detailed understanding of quantum field theory. First of all, this notion that what is quantum field theory has got a misnomer. Now, some people say that it obeys quantum mechanics. Some people say it is special theory of relativity, but it is actually something different. I would like to show you. First, let us understand the very basic and technical decision of what is quantum field theory. So here you see that the classical field theory cannot be ignored. So we have to first take classical field theory. Then the classical field theory first got generalized into whom? That is special theory of relativity of Einstein. That means we have taken the invariance of the speed of light and the observers, etc. So the first unification of classical Newtonian mechanics happened with what? Special theory of relativity. Then what we got? Then we got the next big revolution which came into physics, that is called quantum mechanics. We are not into quantum field theory, understand. So we got into quantum mechanics. Now, when special relativity came into the picture, we have already unified classical law or Newton's laws of mechanics into special theory of relativity. But on the other hand, Werner Heisenberg, Max Born, etc., the pioneer, in fact, even Albert Einstein, as well as Max Planck, has already discovered quantum mechanics. So at one end, we have got classical physics, which is already united with special relativity. On the other hand, we have got what? The quantum world, that is the law world of the small. So now the question to the physicist world was that how can we unite special theory of relativity with quantum mechanics? So having talked about that, as you can see, that quantum field theory is basically an addition of three major theories of physics: classical field theory, special relativity, and quantum mechanics. This contains major three portions. One is that it considers this to be an excited state. That means the particles are considered no more as particles, but a kind of an excitation. That is point number one. Second, as you see, that Lagrangian, I was explaining Lagrangian in the last class, and I will do so more because this is very fundamental. It minimizes to the Lagrangian, and the entire interactions are being shown with Feynman diagrams, which is very crucial. So we have understood that it is a summation of three theories. Particles are considered to be excited states. The Lagrangian, it is reduced to the Lagrangian, and this entire thing is now being shown in what is called the Feynman diagram. Now, here comes a very basic definition, but you need to understand certain important parts. Quantum field theory combines classical field theory, special relativity, and quantum mechanics. But the question is that what is a field? Now, I have actually started first with what is called a classical field theory. Maybe I will make a separate lesson because it is a quite huge one to understand. What is important is the point number one, which you can see. What is a field? Fields are physical quantities that are defined at every point in space and time. And in quantum mechanics, fields are quantized, which means that it can only take one discrete values. Now, this concept of being spread over at one in a space and time where each particular point we can mention, this will change. Field won't be specified that, okay, this is a field and there are certain particles and you are pointing. This will change when we move into Lagrangian. But right at this moment, we will understand field as just a field. It is a field which contains, points which are being discussed, which I was discussing you. And most importantly, that quantization in quantum field theory, fields are quantized. So that means that each can take a discrete area, discrete place. What are particles? Most importantly, particles are localized objects that have a definite position and momentum as per classical physics. What we find in quantum field theory, as I was telling, that particles are excitations of fields. If I go back to this slide, here you can see I told that it is excited state. That means particles are no more particles. They are excited states. So this is very important. So we understood field, what is the concept of classical field, and now we have understood that fields are quantized. This is called canonical quantization, which I think I have discussed, or I will do so in the next lectures also. So that is called canonical quantization. And what are particles? Particles are basically objects that have a definite position and momentum. Here in quantum field theory, particles are basically excitation of fields. We understood this much. I think things are going fine. If you have any question or anything you want to comment, please put it in the comment box. I would love to see that. Okay, next what comes are interaction of forces. Now, quantum field theory allows the description of how particles interact with the other forces. So interaction with one another through the exchange of other particles, we call virtual particles. All these things will come later. And also what is important is that quantum field theory is compatible with special relativity, and it ensures that the laws of physics are the same. Laws of physics are very invariant. Now you see the beauty of quantum field theory is that at one end we are telling that particles are no more particles, they are excitation on the field. We are telling that because special theory of relativity should be merged with quantum field theory, that means Lorentz transformation or the Lorentz invariant in special theory of relativity has to match with quantum field theory. If I go back to my slides now, I would like to quickly summarize. So we understood what is a field. We understood field in terms of classical mechanics and quantum field theory. We also understood what are particles. We also understood that it interacts with forces, and we understood what is the relativistic invariance. That means the laws of nature would be the same. Why? Because it follows the it follows the special theory of relativity. So this is basically the definition, and these are the few very important components in terms of quantum field theory. But the question that arises in our mind is that we all understood that the definition, etc. But my question to you, or rather the question that arose among the physicists, is that why should we learn quantum field theory? Why it is considered to be a very important part in our search of physics. So let us now understand that at all should we learn, we will learn, because as I told you, David Hilbert told, but the question is that why quantum field theory is important. Until we understand why quantum field theory is important, we won't be able to understand further. So from here, okay, so why quantum field theory is important? For that, we need to understand these things. So I would just quickly go through what it is actually. As you can see here, first point is that quantum field theory, what it tells is that it provides a unified framework. That means it provides a unified framework of understanding of the fundamental forces of nature. As we are, okay, physics art is telling, thank you, sir. Okay, so Physics Art, if you're watching, I would request you to please watch till the end, because you are going to get a very easy but a very complete and a comprehensive understanding of quantum field theory, which the books make it very complicated. I'm so sorry to tell, right, Physics Art? So I forgot your name, so please excuse me for that. So he is telling that he is very thankful. Okay. So first of all, what we see here is that it provides a unified framework. Now, you see, as we will see here, that the theory of everything, which is the search, this theory of everything is actually, quantum field theory is one part of TOE, or grand unified theory, or theory of everything, whatever you call. That means in the search of our theory of everything, we got one part. What should be a seminar topic on quantum field theory to present? Okay, this is Devu Goswami. Okay, I really do not understand. Devu, you mean to say you're talking of this, or you would present it in a seminar topic on quantum field theory? If you want, you can let me know now, or let us complete with this today's lecture. You can contact me later in my email. I would suggest you a very good topic, or if you want to do a research paper, also I can suggest you the topic. So the thing is that what I was telling is that the quantum field theory is one part of the theory of everything. I would present, sir. Okay. Okay, fine. So Devu, if you really want, you can contact me at my email ID. It is there right in the bottom, or I can just type it. It is contact.physicsforstudents@gmail.com. You can even contact me in WhatsApp or whatsoever. Definitely, I will suggest you. But I would request you that if you can stay online and hear this out, I think that would be better. You can get a better idea of that. You can contact me later. I will definitely suggest you a very good topic. So Devu, thank you for putting up the comment. And if you can watch it till the end, I will be more happy. So the unification of forces, that is one part which is very, very important. The next thing what we get over here is that, I'm so sorry. Yeah. So the next thing that what we get over here is that explains the behavior of particles at very high energies. That means quantum field theory is basically as an essential for describing and understanding high energy particle physics, including the behavior of particles, how they behave in particle accelerator. So that is also very important, that how things behave in particle accelerator, quantum field theory actually behaves that. Predicts that. So that is why those who are willing to go into particle physics or otherwise also, quantum field theory would be an extremely important understanding, and you can further go into that. Now, the second thing is, you see, predictive power. Now, what do I mean by predictive power is that quantum field theory actually allows, I would say, physicists, not the mathematician, to precisely find out how accurate predictions they can do, because these predictions will be confirmed through experiments. Okay, I just forgot to tell all of you, I will make a announcement soon. You will be surprised to know that on the 3rd of December, I will tell that a very senior scientist from Fermilab, yes, I repeat, from Fermilab, who is dealing with particle accelerator, will be coming live on my channel, Physics for Students, and you can ask n number of questions. She is a very, very senior scientist. I will announce the name soon on the 3rd of December. On the 3rd of December on this channel, and she is directly dealing with Fermilab. She has confirmed, her photograph and all the biodata is with me, so you can do. Now, when I was talking to Dr. Ganguly, she also told that quantum field theory is extremely, extremely important. Without that, in the particle accelerator, where the particles are accelerating, we won't be able to make an understanding. So you see here that this is equally important. And obviously, the next point, you can see that it has helped to develop a better understanding, obviously, because when we talk of quantum field theory, what we understand from here is that it will develop new technologies like lasers, transistors, and many other things. So technologically also, quantum field theory is extremely important. And it actually predicts the existence of quantum fluctuations, for example, vacuum fluctuations, Casimir effect. And I will tell you why the quantum fluctuations, once we come to the concept of transition and spontaneous emission, you will see that the entire Entire space is not free, it is full of virtual particles. And who predicts that virtual particles? Quantum field theory does. So why I am telling you all those things? Because you will understand that this is the importance. Until you understand the importance, it will be difficult for you to carry on the study, and you will feel extremely bored that this is not going to happen and things are not going right. So quantum field theory is a foundational framework that has been incredibly successful in describing the behavior of particles. So at one end, what we got, it is providing a unified theory. It is also behaving the particles at very high energy. It is used to many accurate predictions, even particle accelerators, etc. And it is very much useful for doing technology, typically transistor. You know, this is something called quantum tunneling. Nowadays in pen drive, we do not typically use all those things. We use quantum tunneling, wherein information from here is immediately going to here. So this is what is called quantum field theory and why it is important. Next, what we come is this one, that why do we need a unified theory? Because this is again very important, because until and unless you understand why do we need a unified theory, you won't be able to understand, because this is the mother. Unified theory is the mother and quantum field theory is a child. So here you see what I'm trying to show you. Just a second. Yeah. So here what happens is that it is a unification of three major theories. The first one is called the deterministic behavior of classical physics. Then the next one big was the relativistic behavior. Again, when I talk of relativistic behavior, I would like to mention to all of you, who are those who are watching or who might be watching, relativistic behavior means I am not taking general theory of relativity, mind it. Because if you have attended my webinars, which I conduct every month and I will be doing here, general theory of relativity is not entirely relativistic, rather it is a geometry of space-time. So you see here, that is why relativity till now has been unified with quantum field theory, not the general theory of relativity, only special theory. Because I will show you why special theory of relativity and Maxwell's equations got together, and automatically from here we can easily and quickly shift to quantum mechanics. But general relativity again is not. And what is the reason that general relativity till now has not been unified with quantum mechanics? Because general relativity is not relativity. It is not relativity in true term that it deals with Lorentz transformation. It is the geometry of space-time. It deals with differential geometry and totally a different ball game. You can attend to my free lectures where I provide certificates also in this every month on general relativity. You will have a better understanding. So these are the three areas which has been identified, and till now we have not been able to got into gravity. The reason is that, as I told you, it is not entirely relativistic in nature. I'm going to say it is more or less of a I would say understanding of the space-time. So here you see that why do we need a unified theory? Simple. Because we need a deeper understanding, because a unified theory would provide a more comprehensive and unified description of the fundamental forces of the universe, obviously, and this could lead us to a very deeper understanding, maybe dark matter or whatever, we still don't know. It is very consistent. Why? Because the standard model of particle physics and general relativity are highly successful theories, but they are mathematical and conceptually different. So we or the physicists are trying to get the idea to a more elegant and consistent framework that unifies these two theories, which could potentially lead to a beautiful harmonious theory. But remember one thing also, that the standard model is not a standard model, because the standard model will have its limitations. I will show you what. Solving theoretical problems, yes. Why it is important? Because a lot of theoretical problems, for example, general relativity has limitations, etc. So this can be unified. So the standard model, which does not incorporate gravity and general relativity does not incorporate quantum mechanics, maybe a unified field theory will be help us to get a better understanding. And a unified framework for early universe, it tells that understanding the behavior of matter and forces in the extreme conditions of the early universe, maybe we can develop what is called a quantum cosmology or something else. So that is why we need a unified theory. And there are some mathematical problems with the current theories. As I was telling you, these problems suggest that there is something which is missing from our current universe. Now, what is that something which is missing? We really don't know. So predictions and technological applications, deeper understanding, consistency and elegance, solving theoretical problems, all these are required, and these actually will basically give us into theory of everything. Now here you can see a deeper understanding, a consistent and elegance, solving theoretical problems. Now all those things are a small part of quantum field theory, because quantum field theory has the deeper understanding. Quantum field theory deals with high energy. Quantum field theory is more or less unified with classical special relativity, quantum mechanics. So more or less we are unifying and going towards that. So now the question that arises to our mind is that why quantum field theory emerged? So till now we saw that what is quantum field theory, then we understood that why do we need a unified field theory. Now the question is that there should be a problem, there should have been some kind of an issue that the scientists again have to look into something which is a new theory, which is a quantum field theory. So here you see these are basically the main points. So the point is that, first of all, reconciling with special theory of relativity, which I have actually told you. And then it has got high speed with high energy, because special theory of relativity and quantum mechanics at some point of time was not being able to define things which are moving at a very high speed. I mean to say at a very high energy. So that was again a kind of a limitation. Also, quantum field theory was able to address by treating all particles and fields as quantum entities. And it was success in describing the fundamental problems. And you see here one of the key problems of quantum mechanics was unable to explain what is called the spontaneous emission. So these were basically the reasons that we started to deal with, and quantum field theory emerged out of that. And we will now start to explain a little bit in an easy manner the first ever problem which arose and which we were unable to reply back with the classical mechanics, what is called spontaneous emission. So I will come to spontaneous emission later today in this lecture only, but what I am trying to tell you is that the Schrodinger equation, which is basically we call as the central part of quantum mechanics, this was unable to explain what is called spontaneous emission. This we have dealt in earlier also, but I will just try to give you an overview. Why? Because now first let us understand a little bit intuitively that what is a spontaneous emission. Now you see what happened in typically classical physics, one particular particle and a second particle would interact with each other when there is a medium, when there is an electromagnetic force, or one particle and another particle are coming in contact with each other. But what we found in quantum mechanics, etc., even when there is no force which is present, the particles are interacting. That is what is called a spontaneous emission. Now, this was the problem. Without the interaction of particles, how we can explain it with the usual classical laws? How can we explain? So that was basically the problem with Schrodinger equation, that the subatomic particle transits from an excited state to a lower state, and when it is coming down, it emits a quantized energy in the form of a photon. So you can say that when you are running and running, then you slowly slow down. Why? Because you have exhausted your energy. So these are example, for example, fireflies, luminescent, etc. So here you see in the next slide, what I'm trying to explain is that the electron's energy is not quantized. I mean to say, typically in Schrodinger equation, it is basically a treatment of the classical mechanics. So it is not quantized. On the other hand, what we see that electromagnetic field is also not quantized. So no quantization has been taking place. So quantum mechanics is now going back, or it is requiring for a second theory, which is called quantum field theory. So the excited state of atom cannot decay to the ground state, and the electromagnetism or the electromagnetic force, as you can see, it is not quantized. So these were the two basic problems which Schrodinger's equation eventually was unable to deal with that. So what we see is this one. So in classical physics, as you can see here, the spontaneous emission has been described as, okay, so here we come, okay, I just missed one slide. Yeah, so here it is, spontaneous emission and Schrodinger equation, why? Now, what happens, as I told you, in classical physics, typically in classical physics, if I talk about, then an atom can only emit a photon when if it is already interacting with an electromagnetic field. And in quantum mechanics, an atom can emit a photon even in the absence of an electromagnetic field. This is very important. Here there is a field which is present, here even the field is not present. Now this is because the vacuum state is not empty, it contains lot of virtual photons. And it can interact, these virtual photons, what they can do, they can interact with the atom and cause to emit a photon. Now, spontaneous emission is basically an important process in many areas. And we will now see why Schrodinger equation failed to describe spontaneous emission, because try to understand, it's a very important point, that Schrodinger equation is highly classical. It is the potential energy plus the kinetic energy, it gives the total energy, nothing else. I will show you later, and I will in today's lecture. This is central. Schrodinger equation is just the potential and the kinetic energy taken together. That's it. And spontaneous emission is something which is not taking electromagnetic force. It is spontaneously emitting. So how can Schrodinger equation define that? So here you see in the next slide, what I have tried to show you is that the Schrodinger equation is primarily concerned with the time evolution of quantum states. Remember, Schrodinger equation is basically concerned with time evolution of quantum state, and spontaneous emission is not related to time. It is not related to time. It is spontaneously emitting one after the other. That is the main problem. And the emission process is not adequately captured by the Schrodinger equation, which deals with the deterministic unitary time evolution. I repeat, it actually captures with the deterministic unitary time evolution. That means it is unitary movement. It's moving in one direction. So in order to accurately describe the spontaneous emission, you need to incorporate quantum electrodynamics. And spontaneous emission is probabilistic. That means at any given time, there's a certain probability that an excited atom will emit a photon. So slowly what we are doing is that we are trying to understand the limitation of one theory which resulted into quantum field theory. So particles emission, these are not requiring a field, these are spontaneously emitting, whereas Schrodinger equation is something which is a very classical in nature, which carries an interaction and then only it can explain, whereas spontaneous emission is something which does not require a field. How can Schrodinger equation explain that? So that is basically the problem of Schrodinger equation in order to explain, and that is why we need a quantum field theory. So here you see the time reversible linear equation, and spontaneous emission is something which is called an irreversible process. Right? That means what? That means if you can go in this direction, say for example, if you're going in this direction, you can come back in this direction. Going in this, that is why you see I have shown these two arrows. You're going in this direction and you can come back. That is called a time reversible linear equation. But spontaneous emission is telling that this is an irreversible process. Right? What does that mean? Irreversible is once it is, once it is emitted, it is emitted. You really cannot reverse it back. It is very classical nature. So you throw a cup, it falls down, and with the second law of thermodynamics, again you can go back. But the problem is that here you cannot go back because it is all very spontaneous. Right? So time evolution, this is something which cannot be explained in Schrodinger equation, because it is a time reversible linear equation, and spontaneous emission is something which is irreversible. And that is why Schrodinger equation cannot fully describe it. And to describe it, we need a much more sophisticated theory of quantum field theory. That is the reason why quantum field theory again emerged. Now, here is a point. The basic point is that when we are talking about this time evolution and the concept of time reversibility, etc., what we need to understand is also a very fundamental thing, which I have learned from Professor Leonard Suskind's lecture. And I would like to show you just for a minute, because this is something very central in our understanding. So this is what is called, what is a system? What is a reversible system? So what I'm trying to do over here is that you see that a dynamical law is reversible. That means from point number 1 you can go to point number 2. And from point number 2 you can go to point number 3. And from point number 3 you can come back to point number 2. But what happens that suddenly if you are at point, what happens if you suddenly you are at point number 2? So what happens that means from point number 2 you really cannot say what is your past and what will you be going. This is actually which is called that there must be one arrow to tell where you are going and one arrow to tell where you come from. But if you are suddenly at point number 2, the system is called irreversible system. And this is something which is not allowed in classical physics. You cannot have a system which is irreversible. You see that state 1 has no past and this leads to no future. So what I was telling in this previous slide that Schrodinger equation is a time reversible linear equation. That means from 1 you can go to 2 and from 2 you can come back to 1. However, in a time irreversible system, which is a spontaneous emission system, you cannot do that. You are spontaneously emitting particles and Schrodinger equation cannot do that because classical physics will fail if there is a system which is irreversible. This is actually which is not allowed. So I hope that things are becoming clear. Now, here is something which I would like to tell, that this spontaneous emission, which we understood that due to classical physics, we have something which needs a electromagnetic field, but here things are evolving automatically. Now, this evolvement is basically spontaneous emission, but this evolvement actually has something to do with, and that is what is called a transition rate. It is just a rate. I mean to say, you really don't need to worry about anything, but it is basically just a rate. And this is called transition rate in quantum electrodynamics. So this is actually what is called a Fermi's golden rule. It's a little bit technical. And what it tells is right in front of you. So you can just read it aloud and you can find it what actually it is. So it is from one eigenstate of quantum system if it is going to a group of energy eigenstates in a continuum. So what I would like to tell from here is this one, that if, say, for example, if the Fermi's golden rule that you have already talked about, and if I take the first one, this is I. This is an eigenstate. And remember, this is an unperturbed Hamiltonian, which is H0. And considering the effects of perturbing Hamiltonian, which is H prime, and it is applied to the system. Now, remember that if H prime is time independent, the system goes into those states in the continuum that have the same energy as the initial state. And if H is an oscillating kind of a sinusoidal of a function, then with an angular frequency of omega, it will go as H bar omega. I mean to say the reduced Planck's constant. And in both the cases, the transition probability per unit time will essentially be a constant. So that is why I have written. So here you see the system goes only into those states in the continuum which have the same energy. And for an oscillating sinusoidal, it is a function of time. So, and if I go to the next slide, what you will see is this one. I mean, so this is a little, I won't say it is complicated, but I have actually tried to define all of those things. So you see the first 2 pi arises from time dependent nature of the quantum transition. That means it actually predicts that how the quantum transition will be going. Now, the rest one is called matrix notation between the initial and the final states. And the omega EF is basically the final state. So what the transition probability, it is also called a decay probability. The particles which are decaying. That means spontaneous emission, which is happening in the vacuum, which Schrodinger equation has not been able to define, is now being measured by the transition rate. It is a technical thing. It has got a value which is proportional to the cube, which I have not mentioned to keep things easier. So you can understand the transition rate means the decay, how much this spontaneous emission will be It was actually called Fermi's golden rule, but 20 years earlier, it was Paul Dirac who first actually invented that. After 20 years later, it came to be known as the Fermi's golden rule. Okay. Now, having said this much, what I would like to now go forward is that how is spontaneous emission, I would say, and transition related to each other? How is spontaneous emission and transition is related to each other? So as I told you that spontaneous emission is something which we call it as without the mediation of electromagnetic field, the particles are emitting. That means it is a time irreversible system. However, Schrodinger's equation tells that there should be a present, past, and a future. That means it depends on the classical time reversible system. And this measurement of how much the spontaneous emission would be, that is basically calculated by transition rate, which is a part of quantum electrodynamics. So this is how spontaneous emission, how you measure it, that is basically you do through transition rate. So I hope this part is clear. Okay, now what we come is that what I was telling you, that what is the classical nature of Schrodinger's equation. Now, I'm not going to mathematically derive it, but it is extremely important for people, not only in quantum field theory, if you're going for quantum physics also, you need to understand that Schrodinger's equation is something very classical. Now, I will just show in a very few equations what actually it is. And I'm going to take up, say, for example, average kinetic energy of a particle, and I will just show you those equations one by one so that it becomes clear. So sorry. Yeah. So I would show here the first equation, this one. So here you can see that the average kinetic energy of the particle is this one, right? And what I have done, I hope the equations are now clear, because last time the equations were not very good. And here you can see this K. Okay, let me take a bolder pen. Yeah, this one. So this K, as you can understand, is basically the Boltzmann constant. Now, from here, what we can see is that the square root, that means if I, okay, here it is. So if I take the constant square root, that means if I take, say, for example, b square, and I put a bar over it, and then I take a braces b squared, on the top I put a bar, and then within braces I put 1 by 2. Right. So what happens is that these are called root mean square. So I can definitely put it as RMS, the root mean square. So the root mean square, that means from this equation, we can definitely tell that we get into this equation. Okay. Obviously, it would be VRMS V squared half, it will be this. And this VRMS, what I'm talking about, this part, this is actually the root mean square. This is actually what is called the root mean square. So I think till now the equations are quite visible and you are clear. If you cannot view it, if you need some suggestions, please do put it. Now, at a given temperature, for example, if I take lighter particles and a de Broglie wavelength, say, for example, I can say the root mean square speed of an electron. Classically, I mean to say it can be this one. Okay, let me make it bigger. Okay, so this one is basically what is the temperature and the mass. Just for the purpose of taking, it is a particle, it is an electron, and it shows that 1.5 10 to something like this. Okay, so from here, what I'm trying to measure is that this is basically what is called, it is a given temperature, and root mean square speed of an electron at a room temperature is given. So at a given temperature, in the absence of any disturbing field, the electron will move around randomly. Fine. Now we go to quantum mechanics. Okay. And what we do is that, okay, let me, okay, fine. This is fine. And what I will do is that I will take this equation now. Psi of xt. Obviously, I hope this is very clear. You don't need to worry about. So this represents the one-dimension electron distribution function, and the electron moves within its packet. Now, at a particular time, when the coordinate is, say, for example, let me take the coordinate as x1. just a second, x1 and x2. This one, which one is a bitter one? This one. So I remove this and I try to put this one. So it is x1 and x2. Okay, so this is x1 and x2. I mean to say if the coordinate is beyond the interval in x1 and x2, then the distribution function, this one, it will be equal to 0. So the important feature, what I'm trying to tell is that if this one, this particular equation, okay, looks like a standing wave which is fixed at the both of the end, that means it is just like a kind of a standing wave. This is a standing wave. Okay, so what we can tell is that from this particular equation, psi of xt, which can be written as the product of two terms. So what I'm trying to do is that I'm going to get this equation for you. This one. This is basically, I have taken the classical physics equation. And if we take it, travel along the x-axis in the general form, then we get this. Let me remove this and we get this one. So if this is the classical physics for traveling along the x-axis. So this is the, for example, this is the x-axis, this one. So it is moving in this direction. And this is the x-axis. So we get into this one. Okay. So v is obviously the wave speed. Now, if I substitute the wave function, that means this particular wave function, sorry, if I particularly substitute this particular wave function, okay, this equation, and I put it over here. I'm trying to put this equation over here. What I will get is this one. This one. Okay, what I'm going to get is this one. I hope this is bigger one and this is visible. Okay, so we have just substituted this equation into this equation, and then I'm going to divide both sides by this one. I'm going to divide both sides by this equation, this part. So if I divide both sides by this equation, what I'm going to get is this equation. I hope it is clear now. Where will I put it? Okay, so let me put it over here. Or I think I can copy this into the next one and I can put it here. Yeah. This one is far better, I mean to say. So we got the v as the speed, we have divided this and we got this equation. Okay. Now this equation, remember this particular equation, okay, has only one variable. This particular equation has basically one variable. This is the x variable. It has got just this variable, this x1. Clear till now? Okay. Now, from Einstein's hypothesis, we know that E, why it is not happening? Just a second. E is equal to, I would say, h omega. This is what we know. This is h omega, which is this equation, which I have written. This equation. And we also know this one. This is Einstein's derivation. I mean to say, this we already know. So I can remove this one for you because it doesn't carry any meaning. These codes are better. And what we find is this. Okay, so we know these two things. Clear till now? This we have got this one. Okay, now since the energy and momentum of a photon are originated from the transition of an electron from its high energy to low energy, that means if I can a little bit draw for you, sorry for the bad handwriting, etc. So this is the electron which I have got. This has got a high energy somewhere, and then it is going down and is coming to this state. This is the low energy. So I call it L, and this is high energy, which I call it as H. So the energy and momentum of the photon are originated from the transition of the electron from this energy, high energy, to the low energy state. Okay. So, and the transition process must absolutely satisfy what is called the law of conservation of energy. And the law of conservation of momentum also. So it should follow the law of conservation of energy as well as the law of conservation of momentum. That means we can say that to apply the equations of photon energy of its momentum to the corresponding electron physical quantities, we can use this formula, isn't it? Sorry. We can use this formula. Okay. And we can use this formula also. This formula. So from higher energy to lower energy, we are going that. So we can use this and this. So what we get this one. Okay, let me move it upwards and this one. Right. So what I'm trying to tell you is that because the energy of that photon or the electron has moved from the high energy to the low energy state, right? It has moved from high energy to low energy. So we can apply the quantities of the photon energy of its momentum and the corresponding physical quantities using the formula, this one, omega, this particular formula, and we can use this one also. Using this and this, what we are getting is this one. Clear? Okay. This one is basically the angular frequency and P is basically the momentum. This one is the momentum. And as you know, this h bar is the Planck's reduced constant. So this is the Planck's constant. Okay. Now in classical physics, we already know that the total energy of a system is the sum of the kinetic energy. And I can say, just a second. Yeah. So we can say this one, right? Let me remove this part so it will become better. So we can tell this one. This is basically from classical physics. Okay. What we get is this. And the potential energy, which can be expressed definitely as this one. Okay. So the potential energy E equals to P square 2m E minus U. And from here, what we get is this one. Okay, this is the equation. Okay, so clear up till now, I hope. So what we get is this. Now, substituting this equation, I mean to say, sorry, this won't come here. This would be here. Okay, so from this equation, E equals to P squared per 2m plus U or whatever, we get into this equation, this particular equation. Okay, so equal to 2m by h square. Okay, so from here, okay, let me take forward into a fresh slide. So what we get, if I take this equation over here, let me draw it fresh. Okay, 2m and this one, and then I take this equation, this particular equation over here. Let me put it over here. Yeah. So this one, and we are getting this one, omega square equal to P square S square equal to P square M. And from there, finally, what we get is this equation. What is that equation gone? Just a second. Let me see. Yeah. Right. So from here, if we substitute this equation, what we are going to get is this equation, which I'm going to write because this is a kind of a derivation. What we are going to get is basically h bar square, right, whole divided by 2m. I hope this is visible. And then we get again partial square of the wave function followed by x, and then we get right at the denominator partial of x squared plus what I will get here. I will get the kinetic energy minus the potential energy over here, and then I will get as a wave function of psi x, which is definitely will be equal to 0. Which is definitely equal to 0. Just a second, let me check if I've got this equation right here. Right. So let me just put it over here. This would look cumbersome, so I will just put it over here. Yeah, this is the equation. So I have just written it. So let me put it fresh in the slide. So what we get from here, we get this equation. Okay, this is now visible. From here, what we get is this one. This is known from Einstein's derivation. Then from there, what we get is this one. We substitute the values, we are getting to this. And we know this can be written also as this. I'll put it over here. Okay. And then what we get is this one. So I'm just putting the equations one after another so that now the sequence is visible. We get this further. And we know that this can be also written as this. Right? So as you see, E is equal to P square by 2m plus U, or P square 2m, this one is the same. So we get from here. So E equal to P square by 2m U. I have forgotten, I missed one equation, sorry. I'll just put it below this. Plus U and this one, yeah. So this actually would go here and this would come below. So here it is. Okay. So E P square by 2m plus U, this one can also be written. I mean to say this is OR. This is an OR. This can also be written as this. And substituting this equation in equation number 5, the earlier equation, the equation that we have earlier calculated, this equation. Let me go back and copy this equation, this partial derivative one. I'm copying this, I'm making it over here. This is nice and visible, right? This one, okay, let me put it over here. Okay, this part over here. So what I'm trying to tell is that we are dividing and subtracting, all of these are done. Then what I'm doing is that I'm substituting this particular equation into this equation. This particular equation into this equation. Which one? This one. This one. Let me highlight it so that it becomes clear. This particular equation I have substituted. I have substituted this particular equation into this partial derivative, this equation, and we have got this. Equation number 5. This is this one. So we get this one. This is clear. Okay, so I will carry forward this equation in the next page so that it becomes bigger. Okay. So this is what? This is basically the famous, we call it the one-dimensional time-independent, let me make it big, one-dimensional time-independent Schrodinger Schrodinger equation. This is basically what is called the one-dimensional time-dependent Schrodinger equation. So now you are clear that how do we arrive that. If you want, you can again go back and watch the video or the live streaming. So now what I'm trying to tell is that this is the path for deriving time-independent Schrodinger equation. We can see clearly that the wave function of Schrodinger equation is no longer can be explained by what we call the Copernican's interpretation. It is just an abstract mathematical structure, and it has nothing to do with the reality of the described system. It is highly, so here you can see what I was trying to tell you right from the beginning is that this part is highly classical. This part is highly classical. This is definitely the wave function that we are dealing, but this part actually is basically highly classical in nature. Okay, so what we tried to explain is that the classical nature of Schrodinger equation. Okay, Ottawa joining late. Okay, hi. So somebody from Canada has joined and greeted me. So I just again forgot his name, Robert or George. I'm so sorry. So thank you, and joining from Canada. Okay, so what we get from here, we understood the classical nature of Schrodinger's equation. Okay. Now we also covered, I will just quickly go through it, that what is quantum electrodynamics and quantum chromodynamics. We have gone through that, and we have said that quantum electrodynamics is what describes how light and matter actually interact. And quantum chromodynamics, it is the theory, it is a strong theory of strong interaction between quarks mediated by gluons. So obviously the father of quantum electrodynamics, or you can say quantum field theory, is basically Paul Dirac. So the history of quantum field, the goes back to this. And quantum electrodynamics was able to compute the coefficient of spontaneous emission of an atom. That is very, very important. And the first theory which is in full agreement with quantum mechanics. That is also important. So that is the theory which actually came into with quantum mechanics. Now, the quantum electrodynamics, if I talk, is basically dictated by one particular equation that is called Dirac equation. This Dirac equation came out because, as I told you, as you can see here, this equation is basically what we call the classical nature of Schrodinger equation. All of these equations which I have given, this one, this one, this one, and this one, you see we started with half mv squared. That means we started with classical physics. And then we found the classical wave equation. This is the classical, the classical wave equation, nothing more than this. Okay, let me take it in the next. It will be better for you to see this one if I talk. This is the classical wave equation, and it is coming as an oscillating wave. So what we see, you see that the transition again is very, very important. It is crucial. So from this equation, we are going back to this equation, which is highly, I would say, classical in nature. This is highly classical in nature. So because it is classical in nature, and because it is unable to describe what we called as the problem of Schrodinger's equation, this person, this great genius, Paul Dirac, actually, the Dirac equation made what? It made the relativistic Schrodinger's equation more and more relativistic. That means this particular equation, which we are now dealing about, this is a classical equation, and Dirac equation made this equation very, very relativistic. So in order to make this classical equation relativistic, Dirac actually formed what is called the Dirac equation, right? Okay, so we will move forward what we are covering, because otherwise it would be too late. Here is a quick glance of quantum electrodynamics and quantum chromodynamics. I think I have explained it quite clearly. So you can just, so basic idea is that quantum electrodynamics takes place between charged particles, and here it takes place between gluons. We also covered quantum electrodynamics in our previous lecture, that it is in full agreement with quantum mechanics and special relativity. The first formulation was done by Dirac. Creation and annihilation operators came through. And what happened is that Eugen Wigner, Pascal Jordan, Heisenberg, and Enrico Fermi, Richard Feynman came much later. They actually made the system much more robust. So I hope till now you have understood really the limitations of classical mechanics, Schrodinger's equation, spontaneous emission, problem with time irreversibility, and now quantum electrodynamics is coming into the scene in order to save this. We also went through this, which I am not doing much right now, this that the probability amplitudes and how Feynman's diagram actually extends that. So here you see an electron, a photon is going into one, and electron goes from one place to another, and electron emits or absorbs a photon, so it goes somehow like this. We also found that there are certain problems in terms of divergence and infinities. Now, whenever we are dealing with particularly quantum field theory into very high energy physics, we see that there are a lot of problems with infinities, and we physicists, we really avoid infinity. We really don't want infinities to happen. Why? Because we cannot deal with the mathematics. Here also the same thing happened. Infinities, divergence, etc. happened. So what Paul Dirac's this quantum electrodynamics, so quantum harmonic oscillators, the Heisenberg's uncertainty principle told that the quantum harmonic oscillators cannot remain stationary. which led to the fact that even in a perfect vacuum, there remains an oscillating electromagnetic field. I hope now you come to this point, and this is very clear. Vacuum actually produces constantly photons. And what are those? These are spontaneous emission. What is the problem of the spontaneous emission? Time irreversibility factor. Schrodinger equation cannot define time reversibility factor. So we need to find out something. So Heisenberg's uncertainty principle tells that quantum harmonic oscillators cannot remain stationary. So here you see, and it leads to, even in perfect vacuum, there remains an oscillating electromagnetic field. So has to be Paul Dirac, and this is actually this equation, which is called Dirac's equation. I won't be explaining this equation in today's class, because I will make a separate class where I am going to, impart a little bit of knowledge on Dirac equation. So what is it is, as you see, this is the relativistic part of the Schrodinger equation, which is able to explain spin half particles. It is a very relativistic part, and it was able to describe spin half particles. So what it is, it describes spin massive particles, right? Consistent with both mechanics, quantum mechanics, and special relativity, and it was the validated with, that means it has to be validated. It was validated with the hydrogen spectrum. Now, if I put it over here in a fresh page, okay. So what we find over here, if I make the equation a little bit bigger for you, you already know certain values. You already know certain things. You know what is this one. This is the photon. You already know this one, which is a reduced Planck's constant. You already know this one, which is the speed of the light. You already know this one, psi, which is the wave function. This is the wave function. Only few things remains unexplained that in the Dirac equation, which I will definitely make a video. You can put it in the comment box. It looks nice if you really want to understand what is Dirac equation. However, we will go back to this presentation, and we try to complete it as quickly as possible. So here you see that the renormalization, which was done because dealing with infinities was a problem. Julian Schwinger won a Nobel Prize, Dyson did it, Richard Feynman and Shinshiro Tomanga, and replaced their infinities and by the finite measurement. It might be going in your mind that what is actually a renormalization. Here I would like to quickly explain you, not much, that it actually removes infinities and get a theory which is finite to answer. So if I now again share this part, and if I make a kind of a, say for example, this particular particle coming, it is interacting with particle, this is going outside, it is getting into another particle, it is getting into another particle. So all these particle distributions which you see over here, these leads to infinities. This leads to singularities, and that is the problem. So in order to remove this singularity, we got this one, the Dirac equation, which fundamentally explained a lot of things. It fundamentally explained a lot of things. So this is basically renormalization. So here you see, this is a nice diagram which it tells that electron, it is a field, positron, it is a field, and neutrino. So all the particles are just ripples in the field. And if I go back now to my previous slide where we just started about an hour back, I told that the basic definition of quantum field theory is what? That the particles are excitations in the field. These are not considered as particles. Classical field theory will consider particle as a particle because it will interact, it has electromagnetism, it has got a medium, whatever, and classical physics. But here it is all excitations of the field. And here you see these are the excitation. So here is a mass charge, which is during interaction, it goes into photons. And after the interaction, the mass which started with minus m, say for example, it got into m plus plus. The charge which was C got into CV minus minus. Just into so the different mass and charge. So here you see on the right hand side of the slide, it shows that renormalization actually replaces the initially postulated mass and charge of an electron with the experimentally observed mass and charge. Also, positrons, which are obviously more massive particles, they exhibit precisely the same observed charge as the electrons, even in the presence of much stronger, I would say, intense clouds of particles. So the positrons which are interacting with the electrons observed charge, even in the presence of much stronger particle, renormalization actually moves away the initially postulated mass and charge of an electron with experimentally observed mass and charge. That means interacting with those particles, I mean to say, whatever it is interacting, the particle is coming in, it is interacting with a much more massive charge, and what it is coming out, the final outcome that experimentally provides, and that is, it is removing the infinities and giving something very finite. That is basically the idea, and that is basically the essence of renormalization. So that is what it tells, that the war against infinities had come to an end, and we have established quantum field theory, and we have the problem that arose was finally removed. I will quickly go through what is a standard model in particle physics we covered, because classical fields, special relativity, quantum mechanics unified into quantum field theory, general relativity and quantum mechanics still striving to get into string theory, and electromagnetic strong and weak forces went into what is called a standard model. So what we're trying to build in a safe house where everything will be in a grand unified theory. So I have showed earlier that standard model is basically the elementary particles, which are very fundamental. That means they cannot be further divided. Standard model actually contains of basically two broad areas, fermions and bosons. Fermions can be divided into quarks and antiquarks, and into leptons and anti-leptons. Quarks have up, down, strain charge. This is particle physics. I mean to say, I have not described all those things, which I will do later. And bosons actually have gauge bosons and scalar bosons, and so on. We get the standard model that the fermions, they obey the Fermi-Dirac statistics. That means these are spin half, and they obey the Pauli exclusion principle. That means one after the another, after the another, after that, it can stack up, where bosons, they cannot, because it does not obey the Fermi-Dirac statistics. It obeys the Bose-Einstein statistics. So that is very fundamental in terms of particle physics. So here you can see that 5 elementary bosons, and there are Higgs bosons, which carries a mass, and the force carriers. We also dealt with this, which is called a matter. A matter, for example, a car or you and me, these makes up the quarks and the leptons, and the quarks again builds up the hadrons, mesons, baryons, and so on. And the force carriers are basically gluons, which carry the strong force, binds the quark together. So you see, gluons are the strong force which are binding the quarks together. So if I go here a little bit more, and I try to share this one, so you see, I can just hierarchically draw that these are the protons and electrons, that these are again going into quarks. Quarks are going into this, and then I am you, the human beings are being formatted. So that actually shows, a kind of a hierarchical development of particles, which led into particle physics. So that is basically, I have drawn it. You can, watch it also later. There are certain limitations of the standard model. What are those? The standard model has certain free parameters. Free parameters are something which we take, for example, electron, etc. And these free parameters are not properly defined. The standard model also does not include gravity, and the standard model does not explain dark matter and dark energy. The standard model predicts that neutrinos should be massless, but our experiment shows that neutrinos do have a mass. And if you have seen the live podcast with Dr. Jessica Turner, who is a specialist in neutrino, another specialist coming up, I will surely explain. They have told that experimentally, so standard model also have limitations. It does not include gravity, neutrinos have mass, and it does not explain dark energy. Also, the standard model has these free parameters, so they, must be measured experimentally. That makes it difficult for the predictions to do. So we know what are the fundamental reactions that takes place. The weak, strong electromagnetic force. I'm just quickly skipping because the streaming is already going quite long. So these are very fundamentals which you can see. So gravitational force, electromagnetism, strong and weak force. Gravitational force have a long distance. Strong force deals with subatomic particles. Gravitation is more involved in the curvature of space-time, and so on. The weak force actually is something which is very responsible for the radioactive decay. That is why it is called. Now see, this decay again now can go back to spontaneous emission, because as I told you, spontaneous emission is responsible for what is called a decay. So this decay again is a time irreversible process, and this decay cannot be explained by Schrodinger's equation. So things become very clear, right? So from radioactive decay, we have three types of decay: alpha, beta, and gamma decay. And emits an alpha particle, emits a beta particle, and so on. And this actually was done. Okay, I missed one. This is fine. This is the difference between fusion and fission. And in 1993, actually, Fermi proposed the interaction of electroweak theory. And this was later united in a weak force by Sheldon Glashow, Abdus Salam, and Steven Weinberg, which is called a Weinberg-Salam model. We also got these values of weak force, which has W plus, W minus, and Z0 bosons. So here you can see I have given the giga electron volt. So W plus has either positive charge. So these are spin 1 particles, right? And has got a magnetic moment also. The strong force, obviously, it is very strong. I mean to say, these are called strong force because they hold together the nuclei, because otherwise things will burst apart. So it binds fundamental particles together to form large particles. And as you can see, that proton and neutron, they are binding together. These are the strong force, and these are called color force, which again falls into quantum chromodynamics, which is not a part of us. And from here, what we get is that it is called a strong force. Again, you see here, there is one catch, which most of the students, and they make a mistake, that why gravity is called a weak force. Now, I understand if I bring this one and maybe this one together, there is no attraction, no repulsion, nothing is happening, right? So in terms of that, we can call it as a gravity as a weak force. But if we take two more electrical charges or magnets together or something like that, then it will do some kind of interaction. Also, what is important, you need to understand that I am sitting on the table, there are 100 elephants in this room or whatever. This pressure would not cause enough curvature for Einstein's field equation to detect. It won't cause that amount of curvature. That means I need a huge mass, a Jupiter, a black hole, a supermassive black hole, so that I can measure that curvature through Einstein's field equation. So that is also a reason that gravity is called a weak force. Obviously, two bodies coming together, it doesn't cause any interaction. But also I need a huge mass to cause the curvature to take place. So here you can see this is basically the fundamental interaction which takes place between the nucleus, electron and proton, and quarks are basically strong force are binding things together, and that is why it is called a strong force. So I have shown this one. And finally, this is the last slide. So here you can see I have summarized photon, gluon, W and Z bosons. So spin 1 particle, actually what happens is that the spin 1 particle, I would say they actually follows the Lorentz invariance. Anyway, I will speak to that a little bit details. It's a little bit requires explanation. Mass 0 of the gluons and W and Z bosons. So that actually covers today's, I would say, lesson regarding quantum field theory. I will wait for your feedback. Already, I think you are watching. You can watch it later. In the next video, which will be a live class again tomorrow, I will start a little bit early, say about 7 o'clock. I'm going to explain more about what is called a Lagrangian. I mean to say why Lagrangian is important. This is covered in my lecture number 5. But what happened is that in lecture number 5, I was writing those equations with my mouse. So it was not properly assigned and it is not properly done. So I'm going to revise that. I'm going to show you what is Lagrangian, why Lagrangian mathematically is very important, and from classical Lagrangian, how we can go to Lagrangian density, and how Euler-Lagrange equation can be an equation of Newton's equation of motion. That means F equals to ma can be an alternative from Euler-Lagrange equation. Question is that why do I need Euler-Lagrange, such complicated partial differential equation, if we can explain what we call F equals to ma simply? Definitely there is a reason, and that reason leads us to the next level of quantum field theory, and that is finding the Lagrangian and Lagrangian density. This I will try to cover up in tomorrow's video. I will try to float the time today itself. I will try to start a little bit early, around 7-ish, and I will try to finish it by 8 o'clock. So thank you very much for watching this live today. and you can put up your comment, you can put up your feedback about that. I know it is quite long because video is video. I will put up videos, but live classes are really interesting. Interacting with you all who are watching this video, writing equations and going much more deeper. So that's it for today. Tomorrow I will be coming live around 7 o'clock, and I will try to explain what is the Lagrangian, show you the equations, and get into the further mathematics of quantum field theory. This was a complete overview because before going to mathematics, this is important. Thank you very much for watching the live stream, and we'll be back tomorrow at 7 o'clock. I will float the time and you can watch this. Thank you very much.